Okay, so now we're going to take a look at reaction stoichiometry. This is kind of one of the most important things to be able to do, especially kind of in this section. And all of the next parts are totally going to be based on this. So although this is quick, for the most part, it's kind of the most important. So stoichiometry, it sounds fancier than it is. Basically stoichion from the Greek element and metron for the Greek measure, so measuring elements. And this is how reactions are kind of measured. This is why we talk about moles. This is kind of why we build it up the way that we do. So here is the best toffee recipe, and it absolutely is the best toffee recipe. Anytime you have a reaction, we can turn that into essentially it's a recipe. It's a recipe to create products. So in this case, I'm taking 1 cup of sugar, half a teaspoon of salt, and 2 sticks of butter with heat and stirring. So there's my reaction part of it with heat and stirring until 300 degrees Celsius. 1 teaspoon of vanilla extract yields our toffee. Okay, so from this, we can essentially say, okay, so 1 cup of, here's my sugar. We've got plus half a teaspoon of, there's my salt, plus 2 sticks of butter. Okay, there are my sticks of butter, 2x. So those things together are going to yield our container of toffee. Okay, so here's our toffee. So what happens if I only have half a cup of sugar? Well, if I have half a cup of sugar, I have to have everything else. What happens if I want to make this for a bunch of people? And I want to make this times 4. So we multiply everything by 4. So although these things weigh different amounts and we're used different amounts of these things, ultimately there is a recipe: 1 cup sugar, half teaspoon of salt, 2 sticks of butter, and we adjust those ratios depending how much product we want to get, how much toffee we want to get in this case. So we are using this quantitative information from the balanced chemical equation in order to get what we want. And so that's exactly what we're going to be doing for our reactions. So here, as a chemist, I have this reaction: 2 hydrogen gas molecules plus an oxygen molecule give me 2 water molecules. So if we take a look at this, there are a number of ways that we can look at this. I can say, all right, well, 2 molecules of H2 plus 1 molecule of O2 yields 2 molecules of water. Or I could say, more importantly, we don't usually deal with the molecule level, but we'll say, okay, so 2 moles of H2 plus 2 moles of O2 yield 2 moles of water. I mean, that's what we're getting. That's the information we're getting from these balanced chemical equations. What I can't say is 2 grams of H2 plus 2 grams of O2 yield 2 grams of H2O. So that is absolutely 1,000% wrong. We're talking about moles because each of these things weighs a different amount. Hydrogen weighs less. So 1 mole of hydrogen, or 1 hydrogen molecule, weighs less. In fact, weighs 16 times less than an oxygen molecule. So we have to use moles. We cannot use grams. So the only time you're ever going to see grams is when we're weighing the amounts out, or we're trying to look at what they'll be kind of in the lab. So when we measure out an amount, so we always are going to start. So this is kind of what we call the stoichiometric square. I call the stoichiometric square. So you are going to start with the amount of some type of substance. So let's say I start with the amount of H2. Let's say that I want to figure out, okay, so I've got X amount of hydrogen. How much oxygen am I going to react together to get how much water? So we're always going to start with some amount of substance A. And then we're going to convert that to moles, because I cannot go directly from amount of substance A to amount of substance B without figuring out how many moles we have, because mass doesn't matter. And when I say amount, I mean the amount through concentrations or the amount through masses. We're going to do masses now, but we're going to look at concentrations and other values later. But ultimately, what it comes down to, if I want to go from amount of substance A to amount of substance B, I always have to transition through moles. So amount of substance A, go to moles of A, go to moles of the B, the substance I'm looking for, and then finally the amount of substance B. So we always have to kind of go through moles in order to calculate how much we have. So we're going to do 3 calculations whenever we go from amount of one thing to amount of another. We're going to go from grams to moles, moles to moles, and then finally moles back to grams. So we're going to constantly go through these cycles, and we're going to need molar masses whenever we want to go from grams to moles, or from moles back to grams. And when we want to go back and forth between moles of one thing and moles of another, we're going to use the molar ratio. The molar ratio is going to come from the balanced chemical equation. Okay, so let's take a look at kind of how this actually looks in practice. So the combustion of propane occurs to the following reaction. 1 propane molecule, 1 mole of propane plus 5 moles of oxygen yields 3 moles of CO2 and 4 moles of water. So before we start these stoichiometric reactions, I kind of want to get you in the habit of knowing, basically figuring out what we need, because we need molar masses or we need molar ratios. So whenever you do one of these, it's always good practice. You don't have to do this when you get good at them, but certainly it usually saves you time in the end. So what I want to do is I want to know, first of all, I want to know N, or the molar ratios. And those are just the coefficients out front. So 1 mole of propane, 5 moles of oxygen, 3 moles of CO2, and 4 moles of water. You don't need to do that, but it certainly is helpful. And then we're also going to figure out the molar masses of all of these things. So C3H8 is 44.11 grams per mole. Oxygen, O2, is 32 grams per mole. CO2 is 44.01. Sorry, those are so close together. It's a little, but it's what we got. And 18. So these are all in moles, and these are all in grams per mole of the substance. Okay, so all of those units are what they are. But having this information here is going to make retrieving it when we're trying to do these problems quite a bit easier. So what I've done is I've set aside, I've created a little table, just had moles of substance. Okay, that's going to be for our molar ratios. And then the molar mass is going to be just in order to go from grams to moles. Okay, so I have this reaction. How many moles of O2 are needed to react with 0.3 moles of C3H8? So this is kind of a warm-up question. We know, so the thought process is this, but I'm going to show you how to do it properly with unit conversion. So the moles of O2, I know that if I look at the moles of O2 versus the moles of CH3, actually, I'm not even going to do it that way. We're just going to do it properly. All right. So what I want to do is I want to know how many moles of O2 are needed. So that's what I'm curious about. Moles of O2 are needed to react with, and there's my original number. So that's what I'm going to start with. So let's start with 0.300 moles of C3H8. So I start with moles of C3H8. What we'll notice here on the stoichiometric square is we're not starting with the amount of substance. We're actually just starting with moles, which means I just have to do this one ratio because it's asking just for moles. So I'm just doing this one conversion. I don't have to do all of the steps, but we will do all the steps in the next one. So how many moles of O2 are needed to react with 0.3 moles of C3H8? Ultimately, what I'm trying to do is I'm converting C3H8 into moles of O2, or I'm converting this and I'm asking, well, how much O2 is going to actually react with the burning propane that I have, which is C3H8. So we're going to set up a conversion. I want moles, and this is why it's important to write down what compound we're talking about. Moles of C3H8 on the bottom, and moles of O2 on the top. Okay. So if I were to cancel right now, moles of C3H8 would cancel, and I have moles of O2. So when we use a molar ratio, we are always converting from one chemical substance to another through the balanced chemical equation. So this is the molar ratio based on the balanced chemical equation. And if we look at the numbers, for every 5 moles of water or of oxygen, I would produce for every 5 moles of water, I would produce 1 mole of would need 1 mole of C3H8. So 1 mole of C3H8 for 5 moles of oxygen. And now we quickly do this calculation. Moles cancels. My unit should be moles of O2, which we're looking for. 5 times 0.3 should be 1.50 moles. 1.50 moles, right? Yeah. So there we go. 1.50 moles of O2 is going to be needed to react completely with a 0.3 moles of C3H8. So that's how we use molar ratio. Molar ratio, again, converted from one chemical. So we started with moles of C3H8 and we converted to moles of O2. We did this through the molar ratio. So let's take a look at the next one. And this is more typically what you're going to see. How many grams of CO2 can be produced with 0.8 grams? Okay, so how many grams of CO2 can be produced from 0.8 grams of O2? So let's start with our 0.8 grams of O2. So again, we're going to set up a bunch of conversions. And I can actually start doing before I even plug in numbers, what I can do is I can plug in the units. So I want grams of O2 to go away and moles of O2. So again, I've got to convert into moles first, okay? So 1 mole of O2, 32 grams of O2. Where did that come from? That right there is just simply the molar mass. So that's the molar mass of O2. All right, so step 1. At that point, right now, if I canceled grams of O2, I would have moles of O2. But I want to actually get grams of CO2. So next up, I want moles of O2 to go away because I don't care about it. And I want to go to moles of CO2. Well, when we're changing from one chemical to another in stoichiometry, we're using molar ratio based on the balanced chemical equation. So 5 moles of O2 is equivalent to 3 moles of CO2 in our balanced chemical equation. 5 moles of O2 is equivalent to 3 moles of CO2. So for every 5 moles of O2 I use, I get 3 moles of CO2 out. So there we go. Let's cancel and see where we stand. Moles of O2 goes away, and I would have moles of CO2. We're not yet done. The last step is I want to convert from moles of CO2 into grams of CO2. And that, of course, is done with, anytime we go from moles to grams, molar mass of CO2. So look back at my table, 44.01 grams of CO2 is equivalent to 1 mole. Moles of CO2 cancel, and we are left with our final unit, which is grams of CO2. So let's do the math. So 0.8 divided by 32 times 3 divided by 5 times 44.01, you should end up with 0.660 grams of CO2. Okay, so that's pretty much it. That's how it works. So the same types of questions, we just have to use that molar ratio and kind of set things up. So use the following to answer the questions below. So I want you to balance this equation. Again, we need a balanced chemical equation. So balance the equation and then calculate the number of grams of calcium phosphide that will react with, if we started with 0.5 grams of H2O, how much calcium phosphide would we actually react, okay? And then tell me how much product of each we'll end up with. And then finally, let's verify it through law of conservation of mass. The mass of the reactant side has to equal the mass of the product side. So hopefully that's the only time mass comes into play, is just to make sure reactants equal products. Total mass should remain the same, because we're going to have the same amount of elements on both sides, hence the term stoichiometry. Okay. And then finally, we're going to get into this quite a bit more in the last section of this chapter. We're not just limited to gram quantities, right? As long as we can get to moles, we can figure out how many moles of something else we have in a balanced chemical equation. So first we did mass, we converted to mass, but we could do that through volume. We could do that through volume of a solution and concentration to figure out moles of something. Number of particles, we can figure out moles. So as long as we can figure out moles, that's kind of the basis of understanding the thing we need. So concentrations, when we get into titrations, which we're going to do in class, you can do all of that. As long as you can get moles, you can use a balanced chemical equation to kind of solve for total amounts. And it makes more sense as you kind of do this more and more and more. Okay. All right, good. So get this done. We're going to do a bunch of these in class, and we're going to do more complex ones in the coming days. So great.